So now the next algorithm that we're going to talk about is going to be the heap algorithm. Heap also going to use the divide and conquer strategy. But the problem with heap is that it's not like merge. Sorry, I said heap. Quick. The quick sort is the next one. The quick also going to use a divide and conquer strategy, but the problem with the quick is that quick is not going to always divide the list by half. It's using another strategy to divide the list, and that's called the partitioning. So it's using partitioning to divide the the list to half. The partitioning algorithms have a lot of different variations, right? So the one that the book are going to focus on, and we're going to talk about it, so basically the basic one, is that we pick the pivot, and we're going to try to divide the list around this pivot every time. So we keep going to do that, right? Every time we have a like size n, and then we're finding a pivot, we're dividing it around the pivot, and then we have two array, and then for each of those array that hopefully are smaller size than this. Again, we're going to find the pivot, and we're going to do the things over and over and over again until we get into the problem of size n, all of them. Here in this example, as you see on this slide, it's only going to show the basically for one branch of this pivot. It's not going to go to all the different branches, right? So you have to doing your and whatever you have a number of elements. But here we're just basically just showing you, one round of this finding the pivot. So, and also the finding pivot in our in our quick sort, which is the basic quick sort, is very simple. It's always finding the index 0 as the pivot. So the very first element in the list is always going to be the pivot. So here, the original list that we have is 52938401167. That's our basically very simple array, small array we have. So first element, which is 5, is going to become our pivot. So we have to find all the other elements and arrange them around the pivot. So how this algorithm works is that it's basically going to kind of like finding the do some sort of comparison. We'll go over this partitioning algorithm. That's the partition algorithm that's going to be called. But imagine the partition algorithm is done, and then 5 is going to go to its own position. And every element, the smaller as a 5, are going to go to the left side of it, and every element that's bigger than the size are going to be to the right side of it. So basically what you see on the picture right now is in the second round, or B, is going to show that the first round of partitioning happened. We find the position of the pivot in this list, and we find all the elements that are smaller than the pivot, and they're all on the left side, and all the small elements that are larger than the pivot are in the right side of the pivot. So 5 is showing you the yellow, and everything is the smaller than the 5, or pivot, is in the left after the partitioning, and everything bigger than that is on the right. And then we have to keep doing this for all of these elements. So the next time we have now 2 lists, right? So 5 is already find its own position, so we get rid of it. We have 2 lists, one from 4 to 0 and the other from 8 to 7. We're going to do the same thing. We're going to do partitioning again for each of them. First list we have here, the pivot for that is going to be 4. So we have to arrange data around the 4. And so we have to find all the elements that smaller than pivot in the left, and all the elements bigger than pivot into the right. But since, again, the data is completely random, but since randomly this can happen a lot, that the pivot is become either the larger element in the list or the smallest element in the list. If that happened, then our partition algorithm cannot really work the way we expected it to work, right? It can't really break the problem to the half. So what really happened in this case, in the positions after we're done with the partitioning, is that we create an array of 0 size in the left, in the right, an array of n minus 1 size in the left of our pivot. So the partitioning, sometimes it's not going to work, and that's dependent on the pivot value. If the pivot value becomes the largest element in the list or the smallest element in the list, then we cannot really partitioning the list to the half. But in the first round, it was working, right? In the first round, our pivot was kind of an average value, it was lucky, and so the list divided kind of to the half. But for the rest of this part of this list, it didn't happen. And so it doesn't show in this picture, doesn't show the other part, right? So the continues the partition algorithm for the other part. So that is why you can see that it's not really going to create a completely balanced tree. And so that because of that, it's not really going to work as in log n, because not all the branches are going to have exactly the same height. So we're not always reduce the size of the problem by half. Sometimes we just reduce the size of the problem by 1, which is not really what we expected to see. That's going to make the performance not as well as the merge sort. So when we do all the analysis on this algorithm or the quick sort, we notice that the quick sort is going to, in the best case scenario and in the average case scenario, it's going to act as n log n. But in the worst case scenario, it's really going to act as order of n2. So if you reversed, we have a list that's completely reverse size, it can act as an order of n2. And so that can be problematic for this algorithm. But it still, since in the best and average case for random data is still going to be order of n log n, so we still consider that the algorithm as an n log n type of algorithm. And there are a lot of different partitioning algorithms available that trying to find a pivot that it's going to be always the average of the list. So we're getting to the point that we try to make this lists as balanced as possible when we divide them. So we really have like 2 half-size lists. But it's not always the case, as I said. So how does partitioning work? So we know that you have to pick the very first element as a pivot. The algorithm is worked as the next element after the pivot, we consider this as a low index. And the other element at index in the size -1, the last index, is going to be as a high. So again, we're trying to, this partition algorithm trying to find the position of the pivot in the list and then arrange the other data in a way that all the smaller data that the smaller are pivot go to the left side of the pivot in the list, and all of them that are bigger than the pivot going to the right side. So we're comparing the low with the high. Sorry, we're comparing, so there are 2 while loops. So first, we're going to compare the low, the element that the low pointing to it, with our pivot. We expect that to be always less than our pivot. So whatever low pointing to it has to be less than our pivot. So we keep going in this first while loop. We keep going until we get to an objection. So low pointing to 2, 2 is smaller than 5. So we're good. We're going to increment the value of low. Low is 9, pointing to 9 basically. 9 is bigger than our pivot. 9 is bigger than 5. So that's an objection. So the low is going to stop right there. And then we're going to start with high. High is going to be the size -1. So it's pointing to 7, the last element in the list. Whoever high pointing to it, we expected it to be bigger than our pivot. So 7 is bigger than 5. We're good. We're decrement now the value of high. 6 is bigger than our 5, our pivot. So we're good. No objection. We decrement up high. 1, on the other hand, is less than our pivot, and we don't want that high point an element that is less than our pivot. So this is an objection. So we're going to stop right there. So low is stopped at 9 and high is stopped at 1. And now it's time to do the swap. So we're going to swap the value of low to the value of high. So 1 comes to the index basically 2, and 9 go to the index that high pointing to it. So now we will start again. So low is now pointing to an element that is 1, and 1 is less than 5, less than our pivot. So we're good. We're going to increment the value of low. Low pointing to 3. And we expect anything low point to it has to be less than our pivot. 3 is less than our 5. So we're good. There we go to 8. 8, on the other hand, is bigger than our pivot. We don't like it. We're going to stop right here. There we go, high. High is pointing at this point to an element that is 9, and 9 is bigger than 5. And again, we expect that whoever high pointing to it be larger than our pivot. So 9 is bigger than 5, so there's no problem with that. We decrement the value of high. 0 is less than our pivot, less than 5, so we don't like it. So we're going to stop right there. So now low stopped at 8 and high stopped at 0. So we're going to do swap. We're going to continue again. High, low, again, be back to the low again. Low is pointing to 0. 0 is less than our pivot. We're good. We increment the value of low. Low pointing to 4. 4 is less than our pivot. We're good. We go on another round. 8. 8 is bigger than 5. We don't like it. So we're going to stop right there. So low now pointing to 8 and it's going to stop. Now we go to high. High was to 8, which was bigger than our pivot. Sorry. Yes, because we did the swap, right? So now high is going to decrement, and so high is going to point to 4. 4 is less than our pivot. We don't like it because, again, high has to point to elements that are bigger than our pivot. So we're going to stop right there. And now at this point, so we have to do swap. But before we do swap, we have to think about our stopping point. We don't really have any other data to do the comparison because low and high passed each other. I mean, that means we went over every entire array. We don't have anything else to do the comparison. So basically, stopping point for this algorithm is that whenever the value of high is less than the value of low. And I'm not talking about the value that they point to it, the actual value of high and the actual value of low. Low should be the lower index and high should be the higher index. And whenever they pass each other, that means we don't have any other elements into the list. We did all the comparison what that was possible. So that means we have to stop. We don't do any swapping. And at this moment, we find the position of the pivot. And that's what we expect to do in this algorithm. Part of the algorithm was to finding the position of the pivot in the array. So what is the position of the pivot? Position of the pivot is whatever the high pointing to it. High pointing at 4. So that means that's the position of the pivot. So swapping is now happening, and we're going to swap the 4 to 5, right? So 5 is coming to the position that high pointing to it, and 4 is going to go to the index 0. So now look at this. We have our position of the pivot. We have all the elements that are less than pivot on the left side, and all the elements that are bigger than our pivot on the right side. So we're done with our algorithm, we're done with partitioning, and we find the position of the pivot for 5. So 5 is no longer going to be, we find the position of it, right? We don't have to do anything else for 5 anymore. So we're done. So again, this slide doesn't really show the entire scenario. For this array. What I'm going to do, I'm going to use the same array and same partitioning that we've done with it so far. And I'm going to use my Excel sheet. I'm going to continue, try to continuing this and showing you what's going to happen to the entire list in the quick sort, because again, as I said, it's not really showing the entire partitioning and the entire quick sort and how it works. Only showing the partitioning for the first round. So let's now go to the Excel sheet that I have